Welcome to CO450 Computer Architectures. This is week 2, and this week we're starting to look at data representations. First of all, it pays to have a little recap on base 10 number systems. So number systems or bases represent the way that we use numbers to count. With base 10, we have 10 digits. So we go from 0 to 9. And this is the base system that we use most often in counting. However, there are other base systems, so notably base 2, which is what a computer uses, which simply has 2 digits, 0 and 1. There's also things like base 8 and base 16, which are also used in computing, and we will come on to. So when you first learned about numbers, base 10, you were taught that numbers can be organized into columns, as shown in my little table here. So at primary school, they would have talked to you about units, tens, and hundreds. And we know that as the units column increases, when it gets to a certain point beyond 9, we move one place towards the left. So when we get to 10, we get 1 moves into the tens column and a 0 goes in the units column. And as that column then increases, as the tens column increases, when it gets to 9, so it moves across to the hundreds column to the left, one place to the left, and that then increases by digits as we move up through the hundreds. So as we move through the units, are continually moving up through 0 to 9, and then the tens do the same, and then the hundreds do the same. So as the number increases in size, the digits slowly expand towards the left. And each time they expand towards the left, one column, the number increases by 10, hence base 10. So in this example, H is the hundreds column, T is the tens column, and U is the units column. What's really happening here, and in maths, we can actually say that the units column is 10 to the 0, the tens column is 10 to the 1, and the hundreds column is 10 to the 2. As we continue to the left, that base power increases by 10 each time. So we go from 10 to the 2, to 10 to the 3, to 10 to the 4, to 10 to the 5, and so on, as the numbers move to the left-hand side. And each time they jump across, we are increasing by a factor of 10. So 10 to the 2 we would see as 100, 10 to the 1 is 10, and 10 to the 0 is 1. Anything to the 0 is always 1. So whether it was 2 to the 0, 3 to the 0, 8 to the 0, 16 to the 0, anything to a 0 is essentially 1. Anything to 1, like 10 to the 1 here, is the base number. So if this was 2 to the 1, it would be 2. If it's 10 to the 1, it's 10. If it's 16 to the 1, it would be 16. So it pays to think about how we count initially in base 10, because the same rules will then apply to other base number systems. And we need to understand base 2. We also need to understand base 8 and base 16. But they work in exactly the same way. But the reason I'm recapping on base 10 first, which you are obviously completely familiar with, is just to make sure that you fully understand what are you doing when you're counting using that base 10 system. Because we use it so often, and obviously in day-to-day lives, and since we were at primary school onwards, we were taught it initially, we haven't come back to it. So you don't very often think about how numbers work, the numbers that you use every day, just in terms of the base number. So it just makes sense just to start with this, and then we'll quickly move into base 2 and so on to have a look at other base number systems, data representation. So if we look at a number in base 10, and the number I've got here we would see as 125, we could read the digits singly, so we could say going from the right to the left, 5 to 1, and we'd notice that 5 being in the units column is under the 10 to the 0. So it's really 5 times 10 to the 0, or 5 times 1. So we could represent that number there as 5 times 1, or 5 times 10 to the 0. That's how we'd really see it in maths behind it. The number in the 10 to the 1 column is 2, so we could say, well, that's 2 times 10 to the 1, 2 times 10, effectively. And in the hundreds column, we have 1, so that's 1 times 10 to the 2, and 10 to the 2 would be 100, so 1 times 100. And we could write those out, so we could write it out as 1 times 100 plus 2 times 10 plus 5 times 1. So the number 125 could also be written out as 1 times 10 to the 2 plus 2 times 10 to the 1 plus 5 times 10 to the 0. And mathematically, perhaps that is a better way to actually represent it. We have shortcuts when we work with base 10 number systems because we are so familiar with them and they permeate our lives everywhere. So people have come up with shortcuts. So we understand the number as 125 because we have a whole load of language around expressing these numbers. But mathematically underneath, this is correct. 1 times 10 to the 2 plus 2 times 10 to the 1 plus 5 times 10 to the 0 is the correct way of writing that out as a number. So you can see straight away that even with base 10 numbers that we're very, very familiar with, there are different ways to represent the same thing. So we could say 125, or we could equally say 1 times 10 to the 2 plus 2 times 10 to the 1 plus 5 times 10 to the 0. It's a longer way of putting it, of course, but essentially the results are exactly the same. The number representation is the same, whether you say it's 125 or you say it with the full breakdown of what those digits actually represent. So we've got a little exercise in the exercise sheet for this week, just to get you into the process of seeing base 10 numbers in a kind of different way and writing them out in a different way. Very simple exercise. I will open up the handout and actually do the questions for you so you can see how that works. So this is the handout for this week, and you can see that we have a little recap on base 10 decimal numbers. So what is the correct way to write out the following base 10 number is the question. 45, as we would see it there. The little bit in subscript here, the little 10 after it, that just indicates that it's a base 10 number. And you might think, well, why do we need to represent it as a base 10 number? I know it's a base 10 number. Well, you do in normal day because obviously we don't tend to work with other base numbers at the same time as we're working with base 10. So most numbers we see are at base 10 because that's the number system that we use the most of. But when you work in computing areas or you work in different base number systems, you have to identify which base number system you are actually working with. And we do that with a little subscript number after the actual digits of the number we're representing. So that little 10 there just simply represents that this is a base 10 number. So we could write 45 as we'd recognize it as 4 times 10 to the 1 plus 5 times 10 to the 0, which would equal 45 as we see it in base 10. So that's just another way to represent the same thing. And it's data representations that we're interested in here. So we've got another couple of examples, which I'll go through. So we've got 68 as we recognize it. So if we want to write that out, we could put 6 times 10 to the 1. And we could do that as plus 8 times 10 to the 0. And that would be the same, equal to 68 in base 10. And then if we were looking at this one, so we've got 183. So we'd recognize that we've got 1 of 10 to the 2, 8 of 10 to the 1, and 3 of 10 to the 0. And again, we could write that out in that longer form. So we might write, oops, no, so we've got 1 times 10 to the 2. Plus 8 times 10 to the 1 plus 3 times 10 to the 0, which would equal 183 in base 10. So as the numbers get bigger, we start to use higher base powers. So now we've got 3,549. So that brings in 3 of 10 to the 3. So let's do that. So 3 times 10 to the 3. Plus 5 times 10 to the 2 plus 4 times 10 to the 1 plus 9 times 10 to the 0, which equals 3,549 base 10. Okay, and the last one there, we now got 27,318. So again, we've moved across to use another digit. So the power of this number, the 2, has gone up by a factor of 10. So now we are into 10 to the 4. So this would be 2 times 10 to the 4 plus 7 times 10 to the 3 plus 3 times 10 to the 2 plus 1 times 10 to the 1 plus 8 times 10 to the 0, which would equal 27,318 in base 10. So different ways to represent base 10 numbers using the underlying mathematical principles of the base powers. So 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, representative of each column. So 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, and 10 to the 4 is 10,000. So, as we know, the base 10 system, which we call the decimal system, uses the digits 0 to 9 to represent numbers. If we wanted to put a larger number in column 10 to the n, e.g. 10, we would have to multiply 10 times 10 to the n. For example, putting 10 in the 10 to the 0 column is impossible. So we put a 1 in the 10 to the 1 column and a 0 in the 10 to the 0 column, thus using two columns, tens and units. So in the tens we have 1, in units we have 0, and we're now representing 10, but still only using the digits 0 to 9. If we tried to put 12 in the units column, 10 to the 0, we would have to do the following. We would have to do 12 times 10 to the 0, which would be 10 plus 2. 2 will fit in the 10 to the 0 column, the units column, as 2 times 10 to the 0. But the 10 will have to move left as 1 times 10 to the 1. So we would write it out as 1 times 10 to the 1 plus 2 times 10 to the 0. And it will be represented in this way in the columns. So 1 under the tens column, 10 to the 1, and 2 under the units column, 10 to the 0. Now that we understand something about the base number system that we use all the time, we now start to look at the binary system that computers use. 8 bits is called a byte. Some other terms that you'll hear quite often are a bit, which is the smallest unit of storage in a computer, representing a 1 or a 0. A nibble, a term that's seldom used now, but it represents 4 bits. A byte, then, is 8 bits, and its size is that is usually represented an alphabetical character, such as a capital A, which is 65 in base 10, or 1 0 0 0 0 1 0 1 0 in binary, an 8-bit binary number. A byte can store up to 256 characters. So using 8 bits, we can have 256 different representations for characters. A kilobyte is 1024 bytes. A megabyte, roughly 1000 kilobytes. A gigabyte, roughly 1000 megabytes. And a terabyte is roughly 1000 gigabytes. A word in computing depends on the computer, but it can be 16, 32, or 64 bits in length. So we use the term word to represent a length of binary number. And normally a computer's word length refers to how it processes those numbers and the number of bits that it can work on at any one time. The binary system works under the exact same principles as the decimal system, only it operates in base 2 rather than base 10. In other words, instead of using base 10 columns, 10 to the 0, 10 to the 1, 10 to the 2, we're now using base 2 columns, 2 to the 0, 2 to the 1, 2 to the 2. Instead of using the digits 0 to 9, we are now only using 0 to 1. So as the numbers increase, moving across from right to left, from column to column, they are going up by a factor of 2. So it's 2 times 2 times 2 times 2 as we move across. 2 to the 0 represents 1. 2 to the 1 represents 2, base number system. And then 2 to the 2 would be 4, because it's 2 times 2. As we move further across, we go to 2 to the 3, which would be 2 times 2 times 2, which would be 8. And then following on from that, it would go to 2 to the 4, which would be 2 times 2 times 2 times 2, which would be 16. We notice that the value of those columns will be doubling, timesing by 2, as we move to the left. So we go 1, 2, 4, 8, 16, 32, 64, 128. So here we see the representation of a binary number, 1, 1. And we can see that we've marked the columns appropriately. So we can see we've got 1 under 2 to the 0 and 1 under 2 to the 1. 2 to the 0 is 1 and 2 to the 1 is 2. So in terms of representing this number, we could say it's 1 times 2 to the 1 plus 1 times 2 to the 0, which would equal 3. Because we've got 2 to the 0 is 1, 1 times anything is the same, so it's 1, 1. And then 2 to the 1 is 2, so we've got 1 of 2. So 2 plus 1, in this case, gives us 3. So 1, 1 in binary equals 3 in decimal. Here we have a longer 8-bit binary number. So we have a byte binary number. We can see we've got the columns 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. Those represent decimal representations. So we've got 2 to the 0 is 1, 2 to the 2 is 2, 2 to the 1 sorry, is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7, well, we're simply doubling. So 64 times 2 gives us 128. Now if we look at the number above, which is the binary number of 111000101, how would we convert that to a decimal number? What is the decimal number that represents? Well, quite simple really. We simply need to times the digit within each column by its power. So 1 times anything will be the same as the power of the column. 0 times anything is always 0. So those columns with the zeros in are simply going to be 0. If we did that and then added it all together, we would get the representation for the number. So in this case, where we have 1s, we have to add up the base powers. So we have 1 under 2 to the 0, so we have 1. We have 1 under 2 to the 1, so we have 2. We have 1 under 2 to the 2, so we have 4. We don't have anything under 2 to the 3, and we don't have anything under 2 to the 4. We have a 1 under 2 to the 5, so that's adding on 32. We don't have anything under 2 to the 6, and we have a 1 under 2 to the 7, so we'd add on 128. So in this, to work out this number, we'd be adding 128 to 32 to 4, 2, and 1. So we'd add those all together, and that would give us our decimal representation, as we're about to do. So converting binary to decimal, we actually have multiple methods for doing this. So the first one, which is what I've just kind of outlined, is called positional notation. So for this example, let's convert the binary base 2 number, which would be as 110110001, to a decimal base 10 number. To help us do this, we first need to create a table listing the powers of 2 from right to left. And it is useful when you are working this out, when you're doing the conversion from binary to decimal, that you do this as well. And you put the binary digits under the appropriate column for where they sit. Because by working out the powers of 2 from right to left, you are then just going to simply add them together where there's a 1. So remember, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128. Keep those in your head. You're simply doubling them each time, and after a while, 8 bits like this becomes very easy to recall. So you need to stop when the amount of elements in the list is equal to the amount of digits in the binary number. So we had 8 binary digits, so we only need to represent up to 2 to the 7 and 2 to the 0, 8-bit place. The example number 11011001 has 8 digits. So we go up from our elements of lists, would go up to 128, and from 1 to 128. Now we write out the binary number in the row below the list. We see here. We move through each digit of the binary number. If the digit is a 1, we write its corresponding power of 2 below the line under the digit. If the digit is a 0, we write a 0 below the line under the digit, because 0 times anything is always just 0. 1 times anything is, of course, in this case, the base power. What we then do is add the numbers written below together. So the sum that we end up with in this particular case is 128 plus 0 plus 0 plus 16 plus 8 plus 0 plus 2 plus 1, which gives us 155 in the decimal. So we have a little exercise in order to demonstrate how to do this positional notation. In reality, you don't need to add up the zeros, you just simply add the 1 position numbers. And it's probably the most common way of converting a decimal number using positional notation, converting a binary number back to decimal using this positional notation conversion method. So this is the exercise that we can use in the exercise for this week, the handout, for practicing positional notation, binary to decimal conversion. So the first one we've done for you, just to give you an example, so we're asking you to convert the following binary number to a decimal using positional notation method. So the number here is 011100000. So we represent the number to 8 bits, although the last 4 bits in this particular number are all zeros. So we place those digits in our little table there under our powers so that we can represent each power of each column above in the decimal. So 1, 2, 4, 8, 16, 32, 64, and 128. We then look for the 1 bits and we note down the power of the column that they're in. So we've got 1 under 2 to the 3, so we've got 8. We've got 1 under 2 to the 2, which got 4. And we've got 1 under 2 to the 1, we've got 2. And those are where the 1 bits are. We take those numbers, 8, 4, and 2 in this case, we add them together and we get 14. And 14 is the decimal conversion of that binary number. Now we've got one for us to have a look at. So we've got our little table here. Now this table, by the way, obviously we've drawn this for you, but if you're doing your own conversion on a bit of paper, which you can bring into the TCA, then you can draw out your own tables on that and just simply do the columns and put the numbers at the top. You probably won't bother to put 2 to the 0, 2 to the 1 as well. I'll just put this on there for completeness. Mostly you'll just write out the powers in the decimal. So 1, 2, 4, 8, 16, 32, 64, and 128 above each column, so that when you put the ones underneath, you can easily see which numbers you need to add together. So that's what I'm going to do here. So let's do that from right to left. So 0, 1, 0, 1, 0, 1. Oops. Too far. 0, 0. There we go. So I've re-represented the number here underneath the columns, and then I need to take the numbers that are above it and add it up. So we've got 32 plus 1 under the 8 here, so 8 plus 1 under the 2, and that's it. So we've only got 3 one digits. So we've got 32, 8, and 2 to add together. So let me just make those a little bit bigger. There we go. So 32 plus 8 would give us 40. So plus 2 would give us 42. So this binary number must represent 42 as a base 10 decimal number. And that's it. Nice little straightforward conversion of a binary number using positional notation. The position of the 1 bits essentially notes down the decimal number that they're equivalent to, and we just simply add them together. So let's do another one. So let's again put that number in. So this time we got 1, 0, 1, 1, 0, 0, 0, 1. So again, we can note down our powers. So we've got 1 under 128, 1 under 2 to the 7, plus we've got 1 under 8, or 2 to the 3, and we've got 1 under 2 to the 2, so that's 4, and we got 1 under 2 to the 0, which is 1. And again, bigger so we can see that. We can add those together. So what have we got? So we've got 128 plus 8, which will give us 136. Plus 4 will give us 140. Plus 1 will give us 141. The correct answer there, 141 in the base 10 decimal number, our representation from this binary. Yeah. Let's come down. So here, now notice the binary numbers get bigger the more ones they have, as you would expect. So the highest binary number for 8 bits that you could have would be all ones. So what have we got here? So I think we've got 5 ones, and 0, and 1, and 1. So here we've got 128 plus 64 plus 16 plus 8 plus 4 plus 2 plus 1. So we need to add all of those together to get our conversion. Now I can tell you a little trick here. Where you have all ones in a binary number going from the far left all the way across to the right, like we have here, adding those all together, I can tell straight away that that is going to add up to 31. Now the reason I know it's 31 is because the next power on is 32. And you'll find that when you add up all the powers up to that point, it's always one less than the next base power onwards. So were we to do this, we would find that we would add that up. We could do it, so let's do it. So 16 plus 8 will give us 24, plus 4 give us 28, plus 2 would give us 30, and plus 1 would give us 31. But I didn't need to necessarily do that because because they're all contiguous from right to left there. I know it's one less. So we have 31 here. So then we have 64 and 128. So 128 plus 64 is going to give us what's that? 192. So 192 is what we have here, plus our 31. 192 plus 31 will give us 223. So 223. 223. Now we could actually check that. Here's another little, just a little tip. If you've got all 8 ones, the highest number you can have here with all 8 ones is one less than the next power on from 128. So 128 times 2 will give you 256. So one less than that is 255. So the biggest number you can have in 8 bits is 255. Because we've got 0 here, effectively you could have done this as another type of conversion. You could have taken 32 away from 255 because it's the only 0 there, and that would have given you 223. Simply, also you could add on 32 to 223. 223 would give you 255. So I actually know I've added this correctly that way as well. So just a sort of method to check. So 223. And that's the base 10. A bit bigger. And if we come down, I've one to do. Just do a few. It pays to do a few of these just when you're getting started, just to get yourself familiar. It seems possibly quite challenging when you first do this. But your eye quickly starts to adapt, and very quickly you start to actually represent this. Now I think I've actually got a miscounted. You've got to be very careful not to miscount your digits. So 1 and 3 zeros. And then 3 ones and a 0. Right, too many ones. Be very careful in the conversion there. So what have we got here? We've got 64 plus 32 plus 16 plus 1. It's a little bit bigger. A little bit. So 64 plus 32, well, that gives us 96. Plus 16 will give us 112. So 113 with the 1. I think. Double check. So 32 and 64, 96. And then 106 plus 6, so 12, 112, 113, 113. I do have the answers on these handouts at the back of the handout. So the last sheet, or in the full workbook, it's the last sort of page, has the numbers of these exercises, so you can see the correct answers for them there. So this one, so 0, 1, and you know, if you want to just make up your own combination of 1 digits and work that back, you could check whether they're right or not based on a calculator. The calculator in Word under scientific mode allows you to switch to a binary number. So you could type in your digits, random digits, convert it from a binary using the calculator back to decimal, and check that you've actually got your calculation right. So positional notation, fairly straightforward enough to do. You quickly get into the habit of kind of seeing what you're doing with it, you know, as it comes to you. So 128 plus 64 plus 32 plus 8 plus 2. So what have we got here? So 128 plus 64, that's 192. Plus 32 would give us 124. Plus 8, well, that's going to give us 132, plus 2, 134. Okay, got any more? No, we're going to a different method. Okay, so that was positional notation. So there's a couple of examples, should give you enough to kind of get your teeth into it. It's straightforward. It's just a question of remembering the powers of 2, 1, 2, 4, 8, 16, 32, 64, 128, 512, 256, sorry, 512, 1024, as we go up. Obviously, those numbers get very big when you get up to the very higher powers. So if you get up to like 2 to the 15 or 2 to the 16, then you're into very large numbers, of course. And for the benefit of these exercises, we'll keep them restricted to sort of 8 bits in length, because that's easy to add together, as I've been doing here, as you've seen. So we'll stick to those. So the second method that we cover for converting binary to decimal is a method called doubling. So this particular method doesn't use the powers, so it can be a bit simpler for converting larger numbers in your head, because you only need to keep track of a subtotal, essentially. So you start with the leftmost digit. The leftmost digit we call the most significant bit. So the very left digit of any given binary number is the MSB, or most significant bit. And the reason it's most significant is because it's the largest bit, essentially, because it will be under the highest power. So for each digit, as you move to the right, you double your previous total and then add the current digit to it. So in this particular method, we're just doubling our total as we go, and we're adding in the next bit along. So in this example, we have this binary number to convert, 100111010, and we want to convert that obviously to decimal using the doubling method. So these are the steps that we would take for that. So we take the most significant bit. Now the most significant bit here is 0, and we then double that. So effectively, we always start with 0 and we double it. So anything times 0 is always going to be just 0, and then we add in the binary bit. So the next bit on is 1. So 0 plus 1 gives us 1. That's our subtotal. We then take that subtotal and we bring it down, and we then double that. So we have 1 times 2 plus the next bit on, which is 0. So 1 times 2 is 2, plus 0 leaves us with 2, of course. Bring it down, so 2 times 2 now is 4, plus the 1 bit gives us 5. Bring it down, so 5 times 2, 10, plus the next bit, which is a 1, so that's 11. Bring it down, 11 times 2, 22, plus the next bit, which happens to be a 0, so nothing, so 22. 22 times 2, 44, again we're adding in a 0 bit, so no change to the result, so 44. And then finally, 44 times 2, 88, plus now the last 1 bit, which gives us 89. So in the conversion of this binary, by keeping track of the subtotal from the first digit on the left, the most significant bit, to the last, the least significant bit, adding them in as we go, gave us a conversion of 89. So again, in our little exercise sheet, we have a method, we have an example of this, and we also have some questions for you to do. Well, I'll do them with you here to allow you to try this method out and become familiar with the doubling method. So we can see that on the handout here, we have an example we've done for you. We've converted 00101101 as a binary number, and you can see that we've started with 0. So you always start with 0 as a doubling method. So it's always 0 times 2 effectively, and which is always going to be just 0. And then we can add in the most significant bit. So the most significant bit here is the first one on the most significant bit on the left is a 1. Sorry. So it's going to be 1 to start with. And that's going to be the case in all of these methods. It'll always be 1 to start with. So 1, bring it down. So 1 times 2 is 2, plus the next bit on is a 0, so that leaves it with 2. Bring that down. 2 times 2 is 4, plus the 1. The next bit, that's 5. 5, bring it down, times by 2, plus 1 of the next bit, which gives us 11. 11 times 2, 22. Next bit's a 0, so it remains 22. 22 times 2, 44, plus the next bit, which is a 1, so 45. 45 times 2 will give us 90, plus 0, so it remains 90. 19 times 2 is 180, and that's the conversion. And you can see the binary number actually in this little grid, as we laid it out, actually writes its way out from the most significant bit down to the least significant bit in that way as well. So that reproduces when we get to the end. Those are the bits that we're adding in. So 1 bit at a time being added into the subtotal that we originally created by doing 0 times 2 plus the first bit, the most significant bit. And again, if you're trying to work this out yourself, on your own bit of scrap of paper, draw it out this way. Do it in the columns and the rows as you're seeing it here to keep track of that subtotal. Once you get proficient in this, as we say, looking at a number like this, you can kind of do it in your head. You don't necessarily need to write it all out. But obviously for working things out for the TCAs and practicing, it's good to kind of do it in this format. So let's have a look at the converting this one. So the most significant bit here is 1, of course, so start with that. So that's going to give us 1. So bring that down. So 1 times 2 is 2, plus the next bit is going to be a 1. In fact, sometimes it's easier just to kind of, let's just write those out first so that we know what we're going to add in each time. So I've just written that number out that way. So 1 times 2 is 2, plus 1 is going to give us 3. Bring that down. So 3 times 2, 6 plus 1 is 7. Bring that down. 7 times 2 is 14. 0 remains 14. 14 times 2, 28. Plus 0 remains at 28. 28 times 2 gives us 56. And that's 57. So 57 times 2 114 plus 1, 115. So 115 times by 2 gives 230, so 231. So 231 is our conversion there, using the doubling method. I've got another example here. So in this case, we've got quite a lot of zeros first. So we could just, put them all in, but it would be 0 times 2 plus 0, which would give us 0 and then coming down. So actually, there's no real point in kind of doing that for the 2 zeros here. We're much better off starting at the first 1 bit for that, just to save a bit of extra work. I think in terms of this, I've kind of allowed for extra, but we really just need to start at the 1 bit. So let's write that down this way. So 1, 1, 0, 1, 0, 1. Yeah. So we don't actually need those extra. I was just going to get you to do the 0 times 2 plus 0. Bring it down, 0 times 2 plus 0, but you don't really need to do it. It's worth noting, because that just wastes a bit of time really, because it's only going to actually start to hit into the calculation where you start to actually get a 1 bit, and then it will calculate. So 0 times 2 plus 1, it's the first 1 digit, will of course give us 1. So we don't need so many rows there. So 1. Bring that one down. 1 times 2 is 2, plus 1, 3. 3 times 2, is 6, plus nothing, so it means 6. Bring that down. 6 times 2 is 12, plus 1, 13. And 13 times 2 is 26, plus 0 means 26, and 26 times 2 is 52, plus 1, 53. Now if you wanted to check your answer, if you were unsure, or you thought, well, I think I'm doing the method right, the doubling method, but I'm just slightly unsure. What of course you could do is just use positional notation. So you've just learned positional notation, so we could look at that and actually add up, use that particular method to convert the binary number as well. So if you just want to double check that your doubling method, you're doing it correctly, just use the positional notation method to check the binary number you're working with, and that will help give you confidence. The other thing, just as another little tip, is because 2 to the 0 is 1, if you find a 1 bit in that least significant bit position, then your number will always be odd. It can't be otherwise, because that's a 1 under 2 to 0, which is 1. So there's always going to be a 1 in your calculation, which will always mean, because the others are all even numbers, that will make it an odd number. So if you get an even number in your calculation and you had a 1 bit there, there's something wrong in your calculation. So those two little tricks can possibly help you a little bit. So use positional notation to check, and if you've got 1 bit in the least significant bit, you definitely should end up with an odd number. If you've got an even number, then something's awry. So let's do another one here. So again, I'm not going to bother with the first 2 0 digits, because it will just be 0. I'm going to start from the 1 bit. So again, I'll just write it downwards just to make sure that I'm converting it, or adding it into the doubling correctly. So let's do that. So 0 times 2 plus 1, 1. Bring that one down. 1 times 2 is 2, plus 1, 3. 3 times 2, 6 plus 1, 7. So 7 times 2 is going to be 14. We've got a zeros next, so it's going to be 14 that's going to be brought down, and then it's going to times by 2, it's 28. So I don't necessarily need to add anything in, or I'll put it over here just for completeness. But that was 14, 28, and then 28 times 2 gives us 56. And again, I can see in that least significant bit it was a 0, so it should be a an even number, which it is. So just to give me a bit of confidence. Yeah, 56. So that's the doubling method, and hopefully that gives you enough examples to get a handle on that. And again, just practice it a number of times. Get used to writing it out for yourself in this way, because it's in the TCA, like I say, you can bring in a scrap of paper and you can make notes, and you can do your working out like this. So in the TCA, we tend to test on the working of your method rather than the results. So it's important that you have a handle on your method and how it works, and how it works in this stage. So in the TCA, we might be asking you for a step in the process of doing the calculation. So at this point in the process, what's the subtotal, rather than actually asking you for the answer. Because the thing about the answer is you could just use positional notation, and maybe you're familiar with that for everything. But I want to know that you can actually do the doubling method as well. So it's important that you know both, and you've got both, and you can show the workings for both as well. Okay. So again, what about going the other way then? What about converting decimal to binary? So again, there are two methods for this that we can use. So just as there are two methods from binary to decimal, we've also got two methods for converting decimal to binary. So the first method that we're going to have a look at is a method called short division by 2 with remainder. So for this example, we're going to convert the decimal base 10 number 156 to a binary base 2 number. So what we need to do first of all is write down the quotient, which in this example is 156. So the quotient is a number that we are looking to convert. So we do 156 quotient, and we divide it by 2, which is our dividend. So we take 156 and we divide it by 2, which gives us 78. And because this is this is an even number, we get an exact division. So in this case, we don't have any remainder. So we simply get 78. So 2 78s give us 156 exactly. So our remainder in this particular case is 0. So it's 0 if there is no remainder. If there is some remainder, or is a remainder, then we'd simply need to note that as 1. So anything less than a whole number needs to be written to the right of the dividend. So in this case, we've got 78, so we'd put 0. So there is no remainder in this first step, so we write 0. We now continue downwards, dividing each new quotient. So 78 is our new quotient after it's been divided. After 156 has been divided in 2, we get a new quotient, which is 78. And we divide that again by 2, and we write out remainders to the right of each dividend. And we will stop when the quotient is less than 1. So this is how it would work. So we'd put 156 divided by 2. That gives us 78. And our remainder, and it's the remainders that we want to keep track of, because that becomes the binary number. So the remainder in that case is 0. We take 78 and we divide it again by 2, and that gives us 39. And again, we have no remainder with this, so our remainder is 0. Now we take 39, now this is an odd number, so it's going to give us a remainder here. So divide that by 2, and we get, as you would see it, because you're used to working decimal mathematics, we would get 19.5. Now, what we would really say is we get 19 remainder 1 effectively. So 2 19s would give us 38, and there would be 1 left over, which would be the 39. So it's 19 remainder 1 in maths. So the remainder 1 we write down. And the 19, we don't try and do the 0.5, by the way, it's just the whole number. So 19 divided by 2, which again would be 9.5, or 9 remainder 1 is how we say it. So 2 9s are 18, we have 1 left over. So remainder 1, which then gives us 9 divided by 2, which would be 4. So 2 4s 8, but we have 1 left over, so it's remainder 1. And then 4 divided by 2 gives us 2, no remainder. 2 divided by 2 leaves us with 1, and again we have no remainder on that. 1 divided by 2 would give us effectively 0.5. So we would just simply say, well, it leaves us with 1, the remainder we could write as 1. So starting with the top remainder, we simply write out the sequence of remainders as a binary number from right to left. So we end up with 0 0 1 1 1 0 0 1, and that completes our binary number. So if you were doing this, as you will be for yourself, as you get the remainders, you can write them to the right hand side as I've done here, but also start to write them right to left underneath. So you're actually starting to write out the binary number as you go. Okay. So once the dividend, the new quotient becomes less than 1, then you need to stop, and you just stay with the 1 number you got. So we got 1 in this case, that remains. So the binary equivalent of decimal number 156. And again, you could use positional notation to convert that back. So take the binary number that you've just generated and use positional notation to check that it actually is 156. Or you could use doubling method, because you know both of those to go back from the binary, just to double check that your conversion from the decimal to the binary is correct. So again, we've got some little exercises for you to have a go at. I'll walk you through them. Just to have a go at this short division by 2 with remainder, which is the decimal to binary conversion. So here's the exercise sheet. So we've got short division by 2 with remainder, decimal to binary conversion. Again, I've done the first one for you, just to give you an example. So convert the following decimal number to binary using the short division by 2 with remainder method. So we had 86. So we take an 86 and we divided that by 2, which has given us 43. And of course, there's no remainder on that. So that's an exact figure. So 0 is our first right-hand number for our binary. And actually, you can see it there. So that first 0 would come in at the end there. So we take our new quotient down. So 43 divided by 2 gives us 21. And 21 times 2 would give us 42, of course. So it's 42 off of 43 leaves us 1. So we have a remainder 1. So 21 remainder 1. So 21 comes down, divide that by 2. And again, it's an odd number, so we can get 1 left over. So it's 10 remainder 1. 10 brought down, divided by 2 gives us 5, exactly, no remainders. 5 divided by 2 will give us 2, remainder 1. 2 divided by 2 will give us 1, and again, no remainder there. 1 divided by 2 will give us effectively less than, so we just simply say 0 with remainder 1. And that becomes the last, that 1 actually becomes the last bit within our conversion here. And again, we write it out in that way. So let's do this one next. So we've got convert 109 So 109, so it's an odd number. So if we divide that by 2, what do we get? So an odd number, that just take 1 away from it. 108 is what we're actually looking to convert. Our remainder here is going to be 1. So in this case, it would be 54, remainder 1. So for two 54s, it gives us 108 plus 1, 109. So it's 54, remainder 1. And that one bit we can put just like that. And bring that one down. So 54, divide that by 2. Now this, I know, is going to give us a remainder 0 because it's an even number. So I know that next bit is going to be 0. So 54 divided by 2 will give us 27. And 27, again, I know it's an odd number, so it's definitely going to give me a remainder 1. So if I think about it as like 26, then what's that? So that's 13, isn't it? 13, remainder 1. 13 is also an odd number. So again, I know that's going to give me a remainder. And so I need to think about what, 12, so that would be 6. 6 divided by 2 is an even number, so that's definitely not going to give me a remainder. 3. So 3 divided by 2, again, I'm going to get a remainder on that one. So effectively it's going to be 1. And then 1 divided by 2, well, that would give us 0. And 1. Okay. Now I've got 7 bits there, so I'm just going to add on a 0 at the other end, just to give me the 8-bit word length. So our binary number becomes 10110111. And again, we could check this by doing positional notation or the doubling method, just to convert it back from binary to the decimal and make sure that is actually base 2. Make sure that actually is 109 in conversion there. I'm fairly confident. So let's see, we've got another one here. So another one. So what have we got? So we've got 72. Click on that. So 72 divided by 2. Even number, so there's not going to be any remainder on that one. So 72, that, so we got 36. Yeah, so 36. I'm going to think. So 36, again, even. So it's going to be a 0. So 36 divided by that is 18. And again, 18, even number. That's going to be 9. Let's just put these digits. Good to keep tally of your digits as you go through. 9 divided by 2 is 4. Now we get the remainder, of course. Divided by 2 is 2. 2 divided by 2, 0. And I could say 0 divided by 2. Oh, it's going to give us effectively still 0. Sorry, we would see that as 1 actually. Yeah. 0 with remainder. I would say that's remainder 1. And after that, as soon as we get below 1, then we can just put in the final 0. So that's our binary. So 72, 0, 0, 0, 1, 0, 0, 1, 0 is what we should end up with. And again, we could use positional notation for our doubling method in order to work that out. Would be the way to kind of go back from that. So it's actually quite easy, this one. If you use positional notation, you'll see that this bit is 2 to the 6. Now 2 to the 6 is 64. And this bit, if we count along, we would have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So that's actually 8. So 8 and 64 is indeed 72. So you could check. So last one, let's just do this one. So 124 divided by 2. So again, it's an even number, so 0. So 124 divided 62. So 62 divided by 2, 31. No remainder on that one. So now we're going to have an odd number, so that's going to give us a 1. And let's just out. Here we go. So 15, remainder 1. 15. Odd number, so that's going to give us that. So that'll be 7. And again, we've got an odd number, so that's going to be another 1. So that'll be 3, remainder 1. And again, we've got another remainder straight away. Odd number. So 3 divided by 2, so must be 1. And again, 1 divided by 2. And we would say 1. So just double check. So we got 2 zeros, 1 1 1 1 1, 1 1 1 1 1, and just to give it the 8-bit word length, so 0 there. Now again, just as with this one, it's kind of easy to check as well. I'll just say how I would double check using sort of positional notation very quickly in my head. Let me just put the base on it so we know that's a base 2. Is that I know that this bit is 2 to the 7, that's 128. And I said about the trick that you can do, which just simply says if it's all 1s, it'll be 1 less than that, so that'll be 127, one less than. I also know that these bits are 2 to the 1 and 2 to the 0, so that'd be 1 and 2. So 3 off of 127 leaves me with 124, which that must then represent. So positional notation in my head, just quickly, I can quickly check that using that kind of approach. So there we go. So division number. People get a little bit confused. It's always the last little bit in the calculation that confuses it. So when you get down to 1 and you're divided by like 2 or less, then you think, oh, how does that mean remainder 1? It just does, because we end up with into a negative figure basically. So a negative figure gives us our 1 remainder there. So it's just something to kind of note and be aware of. This last calculation sometimes gets a bit confusing. So what you're really supposed to do is take this 1, when you get down to 1, you just add that into the number, so you kind of get a little L shape. That maybe is a better way to think about it. I think that's probably when you get to 1, stop and use the 1 bit in your remainders here. But because people are thinking about remainders, I carry on and said, well, divide it by 2, and then if it's less than 0, put a remainder there as that 1 bit. So I tried to get it so it'd line up as a number. So I may have slightly fudged it a little bit in that last bit, which I don't know if it's more confusing or less, because sometimes people get confused by saying, when you get to 1, add that into the remainders, or simply divide it and then put a remainder 1 to create your number at the side. So that's a little bit of a fudge on my behalf there. But if you do a few examples like we've done here, you'll see how that's kind of working, and you'll be able to factor that bit in. So the next method of converting decimal to binary, the second method we're going to look at, this is called comparison with descending powers of 2 and subtraction. So what you need to do first of all is list out the powers of 2 in a base 2 table from right to left, as we did before for the positional notation method. So we list out the elements, and then we look like this. So in this time I've got 10 of them. So I've got 2 to the 0 all the way to 2 to the 9, which isn't too bad. You should be able to keep those numbers in your head fairly easily. So 1, 2, 4, 8, 16, 32, 64, 128, 256, and 512. So I've just extended the table beyond the 8 bits that we normally work with, just so that we've got a comprehensive table we can look at in this particular case. And then I've put a binary number underneath. So I've got 0011101 is my binary number that I'm going to convert well, I've got a binary number. Actually, I think why have I got a binary number there? Because we're going from decimal to binary. Okay, no, don't worry about the binary number for a minute. I think that's what we're gonna convert to it. So we want to figure out the greatest power that will fit into the number that we want to convert to binary. So in this example, let's convert the decimal number 156 to binary. So what's the greatest power of 2 that will fit into 156? So we're looking for a power of 2 that is essentially less than 156, not greater than, less than or the same, or equal to, actually, equal to or less than. So 156. So we can't do 256 because 256, 2 to the 8 is larger, but 2 to the 7, 128, will fit within 156. So what we do is we write down a 1 underneath the 2 to the 7 position at 128, and then we take 128 and we subtract it from the decimal number that we are converting. So we're going to take 128 off of 156, and what that's going to leave us with is 28. And then we move to the next lower power of 2. So we say, well, can 64 fit into 28? Well, obviously not, it's bigger. But it's bigger, so we put 0 under it. And then we say, well, okay, what about the next one? So what about 32? So 32 doesn't fit into it either, so that's no good, so we put 0 there. And then we get to 2 to the 4, which is 16. And 16 is obviously less than 28, so it fits into it. And we can then subtract, we can put 1 under 2 to the 4, and we can subtract 16 from our 28. So that leaves us with 12. And then we look at the next power. So 8 is 2 to the 3. So 8 we can take away from 12. So we do that. We put a 1 under that 2 to the 3 position. And that leaves us with 4. And then we see that 2 to the 2 is 4. So we take 4 away from 4, and it leaves us with 0. And at that point, we can just put zeros in the remaining powers. So this is the descending powers of 2 with subtraction. So we're descending down the powers from the point where we started, in this case, was 2 to the 7, and we're subtracting the powers away where they are less than the number that we have to work with from the original subtraction. So it's quite an elegant way, this method of converting from decimal to binary. So I quite like this method personally, possibly more than the subtraction with remainder. So I'd use this one more likely than anything else. To be honest, I just use positional notation all the time, going backwards and forwards. But if I wanted to do conversion from decimal to binary, then this would be my sort of favourite method. So the binary number gets written out underneath using that. It's kind of the reverse of positional notation. So no more powers left in this. You are done. You have 0, 0, 1, 1, 1, 0, 0, 1 as your binary number, and that should be the equivalent of the decimal number 156. And again, you could use positional notation now to check that if you wanted to, by adding up 128 plus 16 plus 8 plus 4, and hopefully you got to that 156 number that we were looking for. So again, we have some little exercises in this week's handout for you to practice with. So comparison with descending powers of 2 and subtraction, a decimal to binary conversion. So as always with the exercise sheet, we've got a little first commands done for us. So in this case, we were converting 57 as a decimal number to the binary. So we looked through our powers. The first power that we could subtract from 57 was 32, so it's less than 32. So we took 32 away. So 57 minus 32 left us with 25. And then the next power was 16. So 25, we can minus 16 from that and put a 1 here. So we just put 1 there. And then that left us with 9. 8 means we can minus that. So again, we put a 1 here. It's left us with 1. And then we can see that 4 and 2 are bigger, so we put 0, and then 1 and 1 away is 0. So that leaves us with 1, 0, 0, 1, 1, 1, 0, 0 as our converted number. Write that. Another one to do here. So 113 is the number that we've been given. So 128 is bigger, so that's going to be remains at a 0. 64 is less than, so we're going to have 1 here. So we're going to need to take our 113 and we're going to need to subtract 64 from it. So 64 off of 113, what's that going to be? He says doing a bit, so it requires a bit of mental maths here. So we got 6, that goes to 17. So now in my head I am thinking that's 36 plus 3. Yes, I'm thinking that's 39. Look at that. So 39. I think I always just double check myself when I do these sort of mental math. If you don't do it for a little while, you get a bit rusty. Oh, no, I've gone wrong, haven't I? It should be 49. 49. Yes. So 49 on that one, I think. Yeah, 49 is what we're looking for. You were slightly off there somehow. So 49. So 32 fits in with that one as well. So again, we can put 1 there, and again take 49 and minus 32 from it. So what does that leave us with? So it would be 8 plus 9, that would be 17. And again, 16 fits within 17. And that's just going to leave us with 1. That's going to be a 0, that's going to be a 0, that's going to be a 0, and then that's going to be a 1, because it's going to be 1 minus 1. So again, we could check that back, and I think I'm going to do that because I just have a little question in my head just to make sure. Like I say, when you're doing this, I'm doing this in my head. I'm not using a calculator. You don't need to really for this. Let's just use our positional notation and calculate that back. So 64 plus 32 gives me 96. And then add on 16, 112. Yeah, 113. There we go. Not too shabby. Sometimes doubt creeps in with numbers. It shouldn't really. It's just confidence. And like I say, though, we don't always do a lot of maths, or at least this type of math, perhaps as much as we should do. We think about it, perhaps. And when you start to think about it, you start to doubt yourself. But there we go. So that one's converted. So let's have a look at this one. 93. Okay, so 128 is much bigger. 64 isn't. So 64 we can take away. And again, what have we got here? So we are going to have so 20, 64 away from 93. That give us so 6, 15, 26, 26 plus 3. Oh, okay. 29. Okay. Write that down in full. So minus 64 equals 29. So 32 isn't going to fit in that one, but 16 will. So 29 minus 16, which will give us 9 plus 4, will give us 13. So yeah. Which 8 also fits within. So 13 minus 8. That's going to leave us with 3. No. Oh, 5. 4 fits within that one as well. So 5 minus 4. 1. So 0. And that's going to be 1. So because it's minus 1. 0. Okay, I think we're there. So again, we could double check. So 64 plus 16. So that's 17. That's 80. Plus 8. 88. Plus 4. 92. Plus 1. 93. There we go. So just to be reassuring that we've got those digits around the right way. So good. Again, I think with these things, the more you sit and do them on the trot, as it were, the more your brain will start to adjust and the pathways coalesce, and quickly you find that your speed mathematics, and you can see that I'm a bit rusty. So I sat here doing it in my head, with possibly the added pressure that I'm recording this, and obviously I don't want to record it all again because I make some catastrophic error. A little bit of pressure there on my own mental math, but you do have to brush off the cogs a little bit. And people say, oh, math is hard. I can't. Anything is difficult if you haven't done it for a while. You need to lubricate the wheels, as it were, in your head, and the only way to do that is by stressing them a little bit to do this math. So I would recommend doing a little bit of practice like this to give you that practice and get the wheels going. So let's do the last one here. So 29 now. So it's not going to be 128, not going to be 64, not going to be 32. It's going to be 16, so 16 away from 29 leaves me with 4 plus 9, which is 13. So let's do that. 29 minus 16 leaves us with 13. 8 will go away from that one as well, so 13 minus 8 leaves us with 5, and the 5 we can 5 we can subtract the 4 from, leaving us with 1, and we know okay. So that again we could double check. So 16 plus 8 leaves us with 24, plus 4, 28, plus 1, 29. There we go. So that gives us a couple of good examples really of using this comparison with descending powers of 2 and subtraction. So now that we can convert between decimal numbers and binary numbers, and back again from binary to decimal, decimal to binary, and we have 2 methods each, so we've covered 4 different methods of conversion. That's really good, so that allows us to work flexibly with them. Let's have a look at a little bit of calculating. So now we can have a look at understand something a bit about addition in binary. So adding 2 binary numbers together is like adding decimal numbers, except that 1 and 1 in binary is going to equal to 1, 0, which is, of course, the representation in the binary for 2. So you effectively able to carry the 1 to the next column, because 2 can't fit in binary representation. You have 0 and 1. So it has to be 0, 1, rather than, we haven't got the 2 digit. So 1 plus 1 in binary would be 0, 1. It is 2 in decimal, of course, but effectively it's displayed as 0, 1 in binary, because we can't represent 2. We have to represent, or to represent 2, we have to move it 1 place to the left. So let's have a look at what we've got here. So just like we would do in decimal mathematics, we can put our 2 binary numbers one on top of the other. So here we have 1 plus 0, which is going to equal 1. I put my carries. These are any carries, anything we need. If we get 2, we're going to have to carry 1 across to the left. And I've just got a carries column. So that carries column there, but row there, is only there to do some working out with, really. Some people put it at the bottom. I've put it above the result in this case, just to kind of make it clear that if I'm carrying anything. So 1 and 0, these are the 2 numbers I'm adding up together. So 1 and 0 is 1. 0 and 0, of course, is 0. So 0 plus 0. 0 plus 1 is 1, and 0 and 0 is 0. So just like in normal mathematics, with decimal numbers, we are just adding the 2 digits together to come up with the next digit. Obviously, if it comes to 1 and 1, that would be 2. Would be 0. Carry the 1 across to the left, as we'll see. So this calculation, we note that 1 plus 1 is 0, 1 in binary. So 1 gets carried to the left to the next column. Let's see that in action. So here I had these two binary numbers. I'm using 4 bits here. So the word length is kind of important for computers. So it's a 4-bit computer. And the word length we have 0, 1, 0, 0, 0, and 1, 0, 0, 0. And we're adding those two numbers together. So the first bit's there, 1 and 1 in both. So 1 and 1 would be 0, and it'd be carrying the 1. So I put that carry 1 to the next column, and we put the 1 in there. So then it's 0, 0 plus the carried 1, which gives us 1. So 1 and 1 is 0, carry the 1, and the next column is 2 zeros, but we have that carried 1 that's come into it, so it's 1. And after that, it's just 0, 0, 0, 0, which of course is 0. So we're not doing anything more with binary addition here than adding ones together. But obviously, if we get 2 ones together, we get 2. And that can't be represented in the column we're in. It has to be carried as 1 to the left, essentially. So let's have a look at another one. So here we've got 1 and 1. So 1 and 1 is 0, carry the 1 to the left. And then we add that into the next column of digits. So we have 1 and 1 again. And now we've got our carry 1. So now you're thinking, oh, panic, panic, we've got 3 ones. Which of course is 3. But how does that work? So let's have a look. So we've got 1 and 1 plus the 1. So effectively, because we've got 3, 1 can go, this would be, if it was 2 ones, it would be 0, carry the 1 again. But because it's 3 ones, we can say, well, it's 0, carry the 1. But that 1, that carried 1, can actually fall in, can be added to the 0, and we can leave us with 1. So it becomes 1 and 1, 1, becomes 1, carry the 1. So again, we move that to the left. And then we have 0, 0 plus the carried 1, so 1. And then after that, we have 0, 0, which is 0. Okay, so don't panic too much. So some people, another way I sometimes suggest is if you got more than 2 ones, do the first bit first. So say the 2 ones, so that would be 0, carry the 1, and then add in the next digit to that 0. So 0 plus 1 would be 1. So that's why that 1 is there, and the carried 1 went across, and that fell into that one basically. So we moved across, shifted across by 1 position to the left as we obviously get beyond 1. So in this particular case, we have a carry in every column. So 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. And then 1 plus 0 plus 1, so it's 1 plus 1, is again 0, carry the 1. So again, we've got some examples in the exercise sheet for you to kind of get your teeth into. Let's hop over there and have a look at that. So in the exercise sheet, we're using 8-bit, 8 word length. You know, our word length is 8 bits to make it a little bit more like a real computer. But the process is exactly the same. And I'm putting the carriers here underneath in this case. So here's my 2 digits. So these are the 2 binary numbers I want to add together. The key is making sure that you put these numbers right on top of each other. So make sure they are aligned precisely, so that the 2 to the 0 bits are lined up, 2 to the 1 and 2 to the 0. What I see some students when they do this, because they obviously will be writing this out on paper, working it out, they get their columns all mixed up, or they get them slightly wavy, so they end up adding the wrong bits to the wrong bits basically, and of course getting the completely wrong result just because he didn't line it up. I recommend blank graph paper for the TCA. So if you can get graph paper as your blank sheet of paper, you're allowed to bring blank sheets of paper in, of course, and pens and pencils to work stuff out. You could just bring a blank sheet and draw columns on it and rows, do a little grid. That's fine. But if you bring in sort of mathematical graph paper and use that, you've already got the columns kind of there. You may still just draw a line as well, but it kind of really helps you to lay stuff out. So let's have a look. So 0 and 0. So we work our way from right to left, just like in decimal mathematics you would do if you're doing addition like this. So 0 and 0 is 0. 1 and 1, like I say, 0, that's 2, so it's 0, carry the 1. I've put the little carry 1 down here. And then you've got 1 and 0, which would be 0, which would be 1, sorry, but you've got the carry 1, so it's 1 and 1, which again is 0, carry the 1, so that carry 1 comes here. And then we've got 0 and 1, we've got the carry 1, so 1 and 1, 0, carry the 1. There's our carry 1 bit. Then we've got 0 and 0, but we've got to add in the 1 bit. So the 1 bit comes in here. And after that, it's just 0, so 0. Again, if you just wanted to double check this, what you could do is, using positional notation or any of the methods we looked at, convert this binary number to a decimal, both of these numbers to a decimal, add them together as a decimal number, work out the result, convert it back to a binary, and double check that it matches the result you got. So the numbers won't change, they still add up the same whether they're in binary or decimal, but you can do a conversion like that just to double check that your answer is correct. That's something just to give you a little tip, really, if you just want to double check yourself. So let's do the next one. So this is the two numbers we have to add together, and just like in decimal mathematics, with binary, it doesn't matter which order you place the numbers on top of each other. Effectively, that'll make no difference to the calculation. So let's just copy these out exactly how they are. And I've just done them in order, so top to bottom. So let's have a look. So 0 and 0 is 0. 1 and 0 is 1. 1 and 1 is 2, so it has to be 0, carry the 1 across to the next column. 0 and 1 plus the 1, so 1 and 1 is again 0, carry the 1. 0 and 1 plus the carry 1 is again 1 and 1, 0, carry the 1. And 0 and 0 plus the 1 is 1, and the rest is zeros. There we go. So our binary number is 0, 1, 0, 0, 0. Oops. 1, 0, 0. This one, I'm going to go put them in the other way. It's just a bit quicker because I have to press my key twice. So let's just put the first number in. And again, just when you're writing these out, just make sure putting all the digits in the right columns. Because I think for a lot of students, sometimes the mistakes that's made, not because they don't understand sometimes, but just they've just got their digits slightly off track. So 0 and 1 is 1. 0 and 0 is 0. 0 and 1 is 1. 1 and 1 is 0. Carry the 1. 0 and 1 plus the 1 is 1 and 1. 0, carry the 1. 1 and 1 and 1 is going to be 1, carry the 1. 0, 0, 1 and 0. There we go. So this was a little bit more tricky because we had these free ones with the carry ones there. So it's 3, which is 1, and then move 1 across. So it's 1 and 2. So 3. So 2 to the 0 and 2 to the 1. So 1, 1. So it was 1, carry the 1. So 1, 0, 1, 0, 0, 1, 1. And again, we could check it by converting those two numbers to decimal, adding them together, getting a decimal number, and making sure the answer is the same. I'll look at the next one. So 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. Oops, didn't move across. 0, 1, 0, 1, 0, 1. Okay, so 0 and 1 is 1, 0 and 0 is 0, 1 and 1 is 0, carry the 1. 1 and 1, because it's no 0 there, is 0, carry the 1. 3 ones here, including the carry 1, so that's 1, carry the 1. 2 ones, so 0, carry the 1, and 0, so that's 1, 0. Okay. So binary addition laid out like this is pretty straightforward to do. One of the reasons, computers can work very, very quickly this type of addition, which is why actually base 2 is really good. It has to do quite a lot of iterations and calculations through, but it's fast because it's only shifting bits really. There are patterns to these bit shifts in order to move, add binary numbers together. So it's very, very quick, although you need quite a bit of it to do more complex calculations, but it can be done quite simply. Okay, so I think that's enough examples of that just to give you the heads up on how to do the addition process. So finally, I've just got a link here, the sort of last part of my presentation, last slide of my presentation, which is about counting, so using binary. And there's a little game that you can play, which is online, learning network, cisco.com, binary game. The binary game is just a fun game, so it's just about trying to make the number, the decimal number, by selecting the appropriate bits within an 8-bit binary window. So if you want to have a go at this, just it helps improve your ability to quickly convert decimal numbers to binary. So I think in the game it comes up with a decimal number, and you click on it gives you a load of zeros, and you click where the ones are going to be in order to make the binary number that equals then the decimal number they've given you, and you get a time limit and so on. It's just kind of probably not the most exciting game in the world, but it does improve your practice, so you can improve your speed doing it. And if you can do that a little bit, you'll get your mindset. So when you get a little bit more practiced at working with binary numbers, you'll find that you can quickly move from one to another very, very easily without too much of a faff. So thank you for looking through this week's presentation and having a go with the exercise questions. This is really the best way to get practice for the TCA. So in the TCA, we test your ability to do all these conversion methods. So make sure you're really up on those. Test yourself, make up binary numbers. They're just a binary pattern. Just try them out and practice over and over again. Practice with a paper and pen. I do not recommend that you sit down with a calculator by your side doing the calculation. Do everything in your head. And again, I know immediately people will go, oh, it's too hard, it's difficult. Well, things are difficult, but it gets easier the more practice you give it. So the more practice you are, the quicker it gets, and the better you'll be, and the faster you'll be at the TCA questions, and obviously the more accurate as well. So practice is really important with this, and that's what I'd emphasize for you to do. So again, thank you very much for your time. My email is there if you want to get in contact with me. Otherwise, have a good week. Thank you very much.